All right, paper chromatography. Paper chromatography is used to separate a variety of mixtures. Now, when I use this term like variety of mixtures, what we are trying to talk about is that we are actually separating two or more solids in a single solvent. All right. For example, let me quote a scenario over here. You mix salt and sugar in water. Now, how are you going to separate them both? Now, remember, we were able to separate sand and salt from water since sand was insoluble and salt was soluble in water. But if we talk about both the things, and both of them are soluble, salt is soluble as well as sugar is soluble in water. How are you going to separate them? Because filtration is not going to work. If you go with crystallization, it would separate both the powders. It would give you actually a crystalline form of both salt and sugar. They won't separate. If you go with
Yeah.
distillation, at the end of the process, you'll get both salt and sugar again. You'll get pure water on the other side. So you can't do simple distillation. You can't perform filtration. You can't perform crystallization. So you need to come up with a process that can separate both of these. Paper chromatography is that process. We at
Yes.
international GCSE level are used to separate mixtures of colored inks or food colorings. They're not just made up of one color, but they actually consist of a mixture of dyes in case of inks and food colorings. Paper chromatography can also be used to separate a mixture of colorless substances, sugars, and then some methods can be used to make spots visible on the paper. We're going to discuss all of that. All right. Before we start a practical investigating the composition of dye with paper chromatography, remember that skin contact with solvents and dyes is not good, especially if you have a sensitive skin. And most of the dyes are not good to touch. We use them in other ways. So anything like gloves can be a very good idea. So let's investigate. Now, what you're going to do is that you are going to perform it in a specific way, since that is not drawn. So I'm going to go with all these steps in the form of drawing. These steps are easier to understand if you draw them. So first of all, you're going to take a strip of paper. This is known as chromatography paper, as mentioned over here. Take a chromatography paper and draw a line with the pencil across the piece of the paper, 1 centimeter from the bottom of the paper. So mark 1 centimeter from the bottom of the paper, and then draw a line across the paper. And you're going to do it specifically with a pencil, with no pen, ink pen, gel pen, or anything like that, since they all consist of dyes and they are going to interfere with the process. So please only use a pencil. So the same thing is mentioned over here. Any pen of colors or inks may move up the chromatography paper along with the solvent. Now, what you do is that you put a spot by putting a drop using a teat pipette or a capillary tube. You draw a small spot on this line like this. It can be a mixture of dyes. It can be two dyes. Let's assume what we're going to do, that we have a mixture of two dyes. We take a blue dye and we take a red dye and we mix them both up.
Yeah.
So let's say our mixture is colored like this. Let's say it becomes of this color, although red and blue do not become orange, since I don't have that option, so I came up with orange. So let's say you marked red, then you can mark a spot of blue, then you mark a spot of red, for blue first, red after, and finally a spot of this mixture. All right. So what I'm going to do is that this is M, you can write it with a pencil, and then this is red, you can write it with the same pencil, and this is blue. Okay. Now, although you don't exactly have to do this, but what you can do is that you can also mark 1 centimeter from here, roughly, and you may mark a line. Since many students will be doing the experiment in the lab, you may write your name over here with the same pencil. Remember, only use the pencil for all of these. The name, this M, this R, this B, the lines, all of this, right? Now suspend this chromatography paper in a beaker that contains a small amount of solvent. So we take a beaker which contains a small amount of solvent, and we actually try to hang this paper over there. मेरा beaker कुछ ज़्यादा ही बड़ा हो गया, so let's shorten up the beaker size. ठीक है? All right. So we just hang the this specific piece of paper in the beaker that consists of small amount of solvent. इसमें थोड़ा सा solvent होगा, like this. So much so that the bottom of the paper just touches the solvent, right? Remember that these lines or these spots should not touch the solvent, or otherwise they're going to simply dissolve in the solvent. And that's what's stated over here, right? If you intentionally put it like this deep in the solvent, these are all going to dissolve over here. So there is no point in doing that. If that happens, you've made a mistake. Restart by taking a new paper strip and then restarting the whole process. All right.
Yeah.
Now, what we're going to do is that we are going to put a lid on top of this. A lid helps because something like watch glass on the beaker and the atmosphere of this entire beaker becomes saturated with the vapors of the same solvent with a little bit of evaporation. All right. The solvent can be anything. This solvent can be water. This solvent can be ethanol. This solvent can be a mixture of many liquids. You can use different liquids. We actually go by a hit and trial method. We try many different solvents and their combination. Whichever one is the fastest for us, we actually mention it in the data. So we have data for many systems and their chromatography over the internet in the form of big books that you can always refer to for different substances. All right?
Yes.
Okay. Now, what happens is that this solvent is going to move up the paper. This is a pretty simple experiment. You can do the same thing at home. Take a tissue paper, right? You don't have a chromatography paper at home. So take a tissue paper. On it, please mark a spot like this with any of your ink pens. It can be blue, it can be black, it can be anything. And dip a little portion of that tissue paper into a glass of water. And you would see that the water rises and it takes along the ink with it. So you can easily perform it at home right after this whole session. Right? And you'd notice the same thing. So you'd notice that this color winds up somewhere over here, and it might have a tail. This color winds up somewhere over here. And for this one, we have the same color over here, and as well as this one over here. All right?
Yeah.
So this will wind up something like this. When the solvent has moved up the paper to about 1 centimeter of the top, remove the paper from the beaker, draw the pencil line to show where the solvent goes. The highest level of the solvent on the paper at any time is known as solvent front. So this exactly doesn't have to be the solvent front. Maybe your the solvent went up like this. So this maximum point is your solvent front. All right. So what are you then supposed to do? Leave the paper to dry so that all of the solvent evaporates. For solvent, you can use water. For non-aqueous, you can use anything else other than water. You may use ethanol. You may use other non-aqueous systems. A suitable solvent is found by a hit and trial method. I've already explained that. So what are we supposed to do after? On the next pages, we have the calculations, but since we don't have enough of this white space on the next pages, so I am going to define those calculations for you. All right?
Yes.
So what we are supposed to do, or what we are interested in, is known something as an RF value. RF actually stands for retention factor. Retention means these colors are going to be retained at some specific point on the paper. Notice that blue retains over here and red goes higher up. right?
Mm.
In order to
Yes.
note down the retention factor, it's pretty simple. It's actually distance. And I'm gonna erase these parts, okay? This one too. So distance traveled by spot over distance traveled by solvent front. All right. And I've already marked the solvent front, so you should probably already know what solvent front is. So as soon as the paper dries, what do we need to do? Take a foot scale or a simple scale that you use in class, take a pencil and start marking these. Now, what are you going to mark? You are going to take up a pencil. So I'm going to do it with black since you would know. So mark it from here to all the way of center of here. This is how much the blue traveled. Let's suppose this was 2 centimeter. All right. Then for red, mark it from
Mm.
here all the way to the center of this spot. And let's suppose it traveled 3 centimeter. For solvent front, from here to all the way here, and let's assume it traveled 5 centimeter. Then the
Yes.
center of this blue, 2 centimeter again, let's say it's 2 centimeter again, and the center of this red from this, and then 3 centimeter again. So you need to calculate different RF values. This is the general formula for RF value. So for RF value for blue spot is what? The blue spot traveled 2 centimeter and the overall system traveled 5 centimeter. So the RF value for blue is going to be 0.4, right?
Can you explain that once again?
So what we simply did is that we calculated these distances from the starting line, and this is our starting line, right?
How
This is
can
our,
you do the measurement?
you're going to take it with the help of a scale you commonly use in class, the meter rule, the foot scale rule. Do you use ruler
Yeah.
scales? Right. So you're gonna
Yes.
put the scale over here and you're gonna properly measure it.
Oh, okay.
I assume the values for the current calculation. I assume this is 2 centimeter, this one is 4.3, this one is 5. Of course, this is not 5 centimeter, this one isn't 3 either, this one isn't 2 either, but I assume these values so that I can show you the working over here. So the RF value for blue spot is 2 centimeter traveled by the blue spot itself, and 5 centimeters the distance traveled by the solvent front itself, right? So it's 2 centimeter over 5 centimeter as per this formula. So our answer is 0.4. Right? And if you are to calculate the RF value of red, how would you calculate it? So tell me the values from the diagram.
Okay. So R is 3 centimeter. I mean,
Right.
the distance is 3 centimeter, and the distance traveled by the solvent is 5 centimeter.
Right. So
Which will be equal to 3 by 5 with 0.6. Yeah.
right. Easy enough.
Yes.
Now we also had the mixture. The mixture turned up with 2 colors, right? So the RF of mixture and that of blue in mixture, right, is 2 centimeter over 5 centimeter. All right, and this is 4. All right, 0.4. And the RF value for the mixture and the red in the mixture is actually the same. And you'd notice these values and all of these calculations are exactly the same. What does this prove you? This proves us that the original blue was also present as a part of mixture. And this original red was also present as a part of mixture. How do we know? Because the spots turned up with the same RF value. All right.
Yeah.
So that's how we compare. Okay, so if this blue and
Oh.
this blue are on the same spot, it means that this specific dye is also present as a part of the mixture.
Hmm. Okay.
All right, do we get the point?
Yes.
Okay, good, good. So now there are many things that we can perceive from a simple paper chromatograph. Now, first things
Hmm.
first, you already know that this blue and this red is a part of mixture because the same colors ended up with the same RF values, almost at the same heights on the paper, right?
Yeah.
One thing.
Yeah.
Second thing, blue only gave us one trail. It means it's probably a pure substance. Red only give us one trail or one color, one spot, which means it's also a pure substance. But M gave us two colors, which gives instantly you the idea that there is this an impure substance, or this is a mixture of two substances. So if you end up with more than two colors, it's an impure substance or a mixture, two or more, of course. And if you end up with just one color or one trail or one spot, it means that's probably a pure substance.
I did not understand the M, like how you explained, like.
M was actually a mixture to begin with, and that mixture contained blue and red. So it
Yeah.
separated both the colors when we went with this experiment. That's the best part of the experiment. Okay, the initial idea of the experiment was to separate the colors in the mixture, right? That's what we stated in the very
Yes.
start, that we would be able to separate the food dyes or food coloring. So now you already know that we have successfully separated red and blue, right?
Yes.
And that's the purpose of chromatography. But that doesn't just end over here. It ends at a point that we calculate the RF value and actually match them with the original ones to give you the idea that this it was not just a mixture. This mixture composed this exact blue dye and this exact red dye, since both of them end up at the same height and give us the same RF value. Clear enough?
Yeah. Yes.
So matching the heights and the spots, their colors and their RF values tells us that are we using the same substance or different. Now let's suppose I am going to assume one more thing to give you a better idea. Let's suppose your mixture gave you one more color. All right, this time it's green.
Yeah.
Now let's calculate. Let's say that this height was 4 centimeter. Then we needed to calculate the RF value of M of G, let's call it green. So this is 4 centimeter over 5 centimeter. So yeah, the answer is 0.8. But when you compare it with the rest of the chromatographic paper, you don't find any other colors of the same spot or at the same height, which means there is something additional present in this mixture M, which has not been used on the rest of the chromatographic paper,
Yes.
which gives us the idea that this mixture probably consists of 3 dyes. We were successfully able to compare it with the blue dye to get a result that this composed of a blue dye that we already have marked with this blue. This mixture also consists of a red dye that we have here and marked with red. But this mixture is composed of one more dye that we cannot mark over here since we haven't used that substance for chromatography in this specific experiment. Make sense? So it's actually comparing the colors, their heights, their RF values. So whether a substance, a specific substance is present, or do we know about that substance or not?
Okay.
So you would safely say that red and blue are both a part of the mixture, but mixture consists of one more substance that we weren't able to identify over here. That's the best part of chromatography. It separates all the substances, so it's easier for you to detect which ones you already have and you performed a chromatography for them, and which ones are left out and you weren't able to perform their chromatography, right? So in the next step, you can perform their chromatography as well.
Oh.
So we can do multiple experiments to find out what our mixture is exactly composed of. It's not just about the separation technique. It's also about the retention factor or RF values, comparing that what the mixture is exactly made up of, right? It's more about detection of substances that mixtures are composed of. Okay.
Okay.
Now, that's why we started off with discussion of dyes. I hope you understand the basic of colors. Now, whenever the student is younger, he or she is about in 3 class or in 4, and that's actually more like a continued discussion, a vertical education form of education. We keep on discussing colors. First, we familiarize a kid with the basic of colors. We talk about red, we talk about yellow, we talk about green, and then we start mixing the colors. We tell them how we can mix red and yellow to form orange, or how we can mix blue and yellow to form green. And then we start talking about secondary colors. We start with primary colors, the 3 primary colors, then we tell them the 3 secondary colors, and then we start giving them more colors, and they get familiar with more colors. And we give them many examples. We give them the example of rainbows. We give them the example of common colors that we use around them in the form of ice creams, candies, fruits, and the list goes on, right? So actually,
Yes.
when we work with dyes, a dye of any specific color is definitely made up of some more primary colors. What if you have a crimson dye?
Yes.
Now, crimson is itself a color that is made up of different other colors. It's actually a mixture of red and orange, right?
Okay.
So this is how colors or dyes are made. We use the primary colors and we add them into different composition to make some other secondary colors. Like indigo is actually a
Yes.
mixture of blue and violet.
Yeah.
Green is a mixture of yellow and blue. And there are many other mixtures that we can talk about. So what happens is that chromatography separates that for us. That's
Oh,
the best
okay.
part. And it's not just about the separation of these colors. We then further need to identify them based upon their height or retention factor they have traveled to for a specific solvent. Fair enough? And this
Yeah.
whole process tells us the fair competition we give them. We put all of them at the same line. We use the same solvent for all of them, and then we let them run along with the same solvent. And then at whichever spot they stop, we compare those spots to get our answers. A pretty good idea, right?
Yes.
Great. So can we move on?
Yeah.
So I'm gonna take a picture of this, right? And I'll send it to you. Okay. So
Okay.
moving on, I'm gonna clear everything up and let's move on. All right, a suitable solvent is usually found by experiment with different ones. The dyes that make up the mixture will be different in 2 important ways. Now, why do they stop at different points on the paper? I'm going to keep this whole of this up. They stop at different points in the paper because of the affinity they have for paper. Affinity means, actually affinity means love. This affinity over here means how well they are going to stick to the paper. So, okay, let's talk about this. Now, I'm going to scroll up a little. Now, when we talk about affinity, remember the one that has more affinity always end up with a less RF value, smaller RF value, travels less on the paper. Since it loves the paper, so it likes to stop as soon as possible. So what can you say for these? Blue has the most affinity for the paper. It likes to stop earlier. Make sense?
Yes.
And green has the least affinity for paper. It does not like to stop earlier. It likes to go as farther as possible. And red is something in between. Make sense?
Yes.
So the one that has most affinity for the paper will have the smallest RF value And the one that has the least affinity for paper will have the highest RF value. I hope you're clear about the concept. Are you?
Yes.
Good.
Yeah.
Then let's move on. There is another point that we need to study, how soluble they are in the solvent. So the more soluble they are in the solvent, or more affinity they have for the solvent, the higher they are going to go up the paper. Now this is opposite for the affinity for paper. All right. So if they have more affinity for the solvent, they love to travel with the solvent, and they go as farther as possible. So what can we safely say?
Yeah.
Green has most affinity for the solvent. You can say the green dye is most soluble in this specific solvent. Since it was able to travel as farther as possible, so green has most solubility. It is most soluble. The red comes in the center, in the middle. It has a somewhat mediocre solubility, and the blue has least solubility. So smaller the RF value, lesser is the solubility, larger is the RF value, higher is the solubility.
Yeah.
Since now it's pretty easy to understand, the ones that has the affinity for paper stops earlier. The one that has affinity for the solvent keeps moving on with the solvent and stays closer to the solvent. Look, solvent stopped over here, green stopped over here, right? So yeah, it has most
Yes.
affinity for the solvent. So it means it's most soluble in the solvent. So this is the kind of questions that we can actually answer after we have a proper chromatographic paper with the experiment complete. And to be honest, we actually call it a chromatogram. Once the experiment is complete, you're not going to call it a chromatography paper. At the start of the experiment, it is a chromatography paper. At the end of the experiment, it is a chromatogram. The name for this paper, for which we have calculated the RF values, is chromatogram, not chromatography paper.
Okay.
All right. So this is a
Yes.
chromatogram. So a chromatogram actually gives you a lot of ideas. It tells you what the mixture is about, how many components the mixture is made up of, what were the RF values. It also tells which component has more affinity for the paper. It also tells you which component has more affinity for the solvent, or which means which has a higher solubility, which one has a lower solubility. It tells you a lot of things. And you should be able to identify those things once you have a chromatogram in front of you. And I actually solved these with numbers to give you the idea how you're going to work that out. All right.
Okay.
Also, from
Yeah.
these calculations, you must have an idea that RF value has no units. Since we keep cutting out the units, since the numerator and the denominators have the same units. If you calculate numerator in centimeter, you also calculate the denominator in centimeter. So yeah, centimeter and centimeter cancel out, and you have a simple number that you can see for all the values solved over here. All right. There is one more thing that you
Yeah.
need to know. RF value is usually less than 1. Since solvent front is able to travel always farther than the dyes or than the spots themselves, so the value is always smaller than 1. So the value is 0.8, 0.9, 0.6, 0.4. If the value is exactly equal to 1, that means the solvent front and the spot traveled the same distance. That means probably you have done something wrong with the experiment. You might need to redo the whole experiment with a different solvent to get a better idea.
Okay.
All right. So the RF value has to
Yeah.
be smaller than 1. Sometimes in papers, they do tend to write units with RF value. What happens is sometimes in the paper, you might be able to see 0.4 centimeter. These units doesn't exactly mean these are the units for RF value. What they tend to write these units for is that you'll get the idea that in what unit exactly your calculations were made. This is to give you the idea that the calculations were made in centimeter. This exactly isn't the unit for the 0.4. This is for the idea that student would know that the calculations were made in centimeter. Because if this is too small, you can make the calculations in millimeters. If this is appropriate, you can go for centimeter. If it's a little big, you can calculate in inches. Different parts of the word we can calculate in different units. So this is to give you the idea what exactly the calculations were made. All right. So don't worry if they write 0 centimeter long with 0.4. It's actually for a better idea of the student. Make sense?
Okay.
Good.
Yes.
Good. Now, do you understand the whole experiment and everything related to it? Can we move on?
Yes.
Okay. So they are going to discuss the figure. Now they're going to discuss the figure and the affinities. Also, he told you that we call it a chromatogram. Not just that. Sorry. We are going to go with the key points. So I'm going to clear it up. If the dye does not move from the pencil line during an experiment, that dye is not at all soluble in the solvent that you are using. It's a very important point. In this case, you need to do it with a different solvent. Redo the whole experiment with a different solvent. If the dye isn't soluble in water, it won't move or budge from its original place with water. Use a different solvent. Use something non-aqueous. Use ethanol. Use methylbenzene. You have a lot of solvents in the lab that you can use or test it for. All right. If the dyes move up the paper with the solvent front, the dye is too soluble in that solvent. And again, you have to try a different solvent. This is the case that I discussed with you earlier. The first case is not the one that I discussed before. So both of these points are important, which means if I do it on this experiment exactly, if the dye stays over here and does not move, you mean if you'll see this portion dark, that means the dye is not soluble. It doesn't even started moving from its own place. If the dye ends up here along with the solvent front, in both the cases, you need to redo the whole experiment with a different dye. If it's too soluble or if it's insoluble, perform it with a different solvent. All right?
Yeah.
Okay. So let's move on. Now they are discussing about these dyes. I'm going to ask questions from you about this. You can say figure 2.11 in front of you. Now, let me know which spot or which substance has most affinity for paper.
It's spot A.
Think again, because you're not right.
Wait, really? Okay. Can you repeat the question once again?
I'm asking for the affinity for paper. Which spot has the most affinity for paper? Most affinity, maximum affinity for the paper. And remember, the spot
C?
that, yes, it's C. Why? Because it stopped earlier. It stopped closer to the starting line, right?
Okay,
the one
so
that
if,
loves the paper loves to stop as early as possible. It does not move much. And the one that moves much has maximum affinity for the solvent. We say it's most soluble in the solvent. In this case, which spot is most soluble in the solvent?
A.
Right, now you're correct. I hope you get the idea, right?
Can you just say me again, like if the spot like C, if it moves, I mean it stops the fastest, so it is called what?
It has most affinity for paper, or you can say it's least soluble. Both things are right.
Okay, yeah.
So
okay.
I'm going to write that over here so you get the idea. We write two things about C. Most affinity for paper. All right, that's why it stopped earlier. You can also say this one is least soluble in solvent. All right. So that's why it stopped earlier. In case of A, we're going to also write two things. Least affinity for paper. It never loved the paper, so it tried to move as far on the paper as it could. Or in other words, it was most soluble, right? So it loved to move with the solvent.
Okay.
I think now you get the idea, right?
What about B?
It is something in between. It has some affinity for the paper, At the same time, it's not as less soluble as C is. It is definitely more soluble than C, but less soluble than A.
Mm-hmm.
So for solubility, for B, it is B is more soluble than C, but B is less soluble than A. We can write it like this. This goes for B. Since it explains A is more soluble than B, but B is definitely more soluble than C. That's why B lies in between A and C.
Okay.
Good. In this example, the
Yes.
mixture must have contained a minimum of 3 dyes. This is the minimum number of dyes. This mixture contains at least 3 dyes because it's giving us 3 different spots.
Yeah.
All right. Why are we saying minimum
Yes.
again and again? Why? Because it is possible that one of the spot is made up of 2 dyes. This may happen that this spot is made up of 2 dyes. So it might be possible that this spot originally consisted of 4 dyes. 2 stopped at the same point and the other 2 stopped at different points. So yeah, minimum of 3 substances. And it can happen that 2 spots coincidentally can save at the same point. How would you know? You could only confirm this by doing an experiment again with a different solvent. So doing experiments with different
Okay.
solvents always gives us the idea, better idea about what the mixture is made up of.
Yeah. Okay.
Right? Okay.
Yes.
So moving on, I'm gonna erase these all and then I'm gonna take a picture. Okay, let's move on. This is an actual one. I usually tend to ask my course students questions from this one. If it was present in a better picture, I might have asked you a lot of questions from it. Okay, yeah, we can ask questions from this one. All right, so I'm going to clear all
Yeah.
of this up. And now, in paper chromatography, you identify the particular dyes in a mixture. In our mixture, which is represented with M, we have the dyes named with D1, D2, D3, and D4. We carried out an experiment and the chromatogram is given right in front of you. You have the starting line, you have the solvent front, you have different of these calculations given in front of you. Now,
Yeah.
which dyes does this mixture contain? M consists of what?
M.
Yeah. Does M contain D1? Compare and then let me know. Okay. How do you do that? Take a look at D1. D1 gives you this spot. Do you have the same colored spot at the same height for M? You do, right? So this means M
Sorry. Can you?
definitely consists of D1. Make sense?
Oh. Okay. So we should. No. 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 Can you
Yeah,
repeat once again?
yeah. You are supposed to give them a fair comparison. So I'm going to clear out it all. Now, I asked you whether D1 is a part of M. How would we know? Now, take a look at D1. This is a pure species. It gave you just one spot. Now, try to put a ruler scale along of this. So at the same height, if you get the same color, it means D1 is a part of this mixture M. Now, answer me
Okay.
this. Does M contain D2? Yes or no?
No.
Does M contain D3? Yes or no?
D3.
This is the spot for D3. This is the spot for D3, the green colored spot.
Yes.
Does M contain D4?
Yes.
Yes, you're correct. You were correct with D2. You are still correct with D3. But what about D4?
Yes. It
Right.
does.
So you have the same height and the same color over here. You have the same height and same color over here, but you don't have anything over here. So you now know that M consists of D1, it consists of D3, it consists of D4, but D2 is not present in M. right? So
Okay.
chromatogram like
Yeah.
this can easily give the idea that what does the mixture contain and what it doesn't contain. And it comes with a simple
Mm.
comparison. It's a pretty easy comparison. You looked at the same lines and the same colors, whether they were present over there or not, right? Are
Yeah.
we clear with this practice? I hope you can do that if a question like this comes in the exam.
Yeah.
Okay, now I'm going to ask you another set of questions. Since you're familiar with these ones, so let's go with another set of questions. Which dyes among
Okay.
these, D1, D2, D3, or D4, is most soluble in this solvent?
Wait, I'll see.
We're
Most
only talking about,
soluble,
yeah,
right?
we are only talking about D1, D2, D3, and D4. We're not talking about the mixture. So which among these is most soluble in the solvent that we have used?
Mm, wait one sec. Most soluble, right?
Right.
So, um,
Do you need a hint?
yeah.
Okay, let me tell you that the one that is most soluble travels maximum farther on the chromatogram. It covers the maximum
So,
distance on the chromatogram.
so is it D3?
Perfect. So on the similar note, which one is least soluble? If D3 is the most soluble, which one is the least soluble?
D4.
D4, perfect answer. All right, let's put the same question in a different manner. Which one has the
Mm.
most affinity for paper? Now, it's the exact opposite question. Most affinity for paper means that it is going to stop as early as possible and travel the least
Okay,
distance,
so it's D4.
right? And which one has the least affinity for paper?
Mm, uh, it's D3.
Right. So it was always about D3 and D4 since either one of them has traveled farthest or least on the paper. All right. So now you know the
Mm.
answers.
Yeah.
Good enough. So in
Yeah.
whichever way they ask the questions, you can always come up with the answers. They may also ask you to actually pick up a scale and go calculate their RF values. Can you? You then need to calculate this
Yeah.
distance for solvent front. If they ask for the RF value of D4 from center of this to this, if they ask for D3 from center of this to this, they've already marked X and
Mhm.
Y for D3 so that you would know Y is solvent front and X is the distance traveled by the spot D3. You can do the same with D4
Mm.
or D2 or D1, right?
Yes.
Good, good, great. So if you can do all of this, you can probably answer every single question that we usually face across in case of chromatography. Now, retention
Mm.
factor it has also other names such as retardation factor. And your book uses the word retardation factor, and they have given you the formula, they have given you the whole thing and how to calculate their answers, right?
Mm. Yeah.
Good, good. So all of these details are something that we have discussed previously. This shouldn't be a problem. He also calculated for other spots, blue spot, orange spot, green spot, all of those spots, D1, D2, D3, D4, for all of
Mm.
four RF values, right? He also explained
Yeah.
that you are going to conclude these for the mixture. Mixture has D1, D3, and D4. The mixture does not have D2. We've already concluded that. He also tells you that the RF value must be in between 0 and 1. If you get a bigger number, you haven't probably divided the numbers in the right way. And RF value has no units, right? Because the units are cancelled out. Okay.
Yes.
So it tells you all the pieces of information that I've told you before. Now, he tells you actually a couple of precautionary steps for it in the last paragraph. Let's go through that. You have to be careful when using RF values as they depend on the solvent used, also on the type of paper. There was no problem in the experiment described above because the mixture and the individual dyes were all put on the same piece of paper. However, if mixture was
Yeah.
put on one piece of chromatography paper and individual dyes were on a separate piece, you can still compare RF values as long as you use the same type of paper and the same solvent. If you use a different solvent or a different type of paper, everything changes. Then that's not a fair comparison. And I hope you understand, in science, experiments require a fair comparison, not just in science, in every competition. For example, if you set the paper, you don't know any questions from the paper. Every question is like a surprise for you. And I'll allow some other student to cheat a couple of questions from the paper. It won't be a fair comparison. So why do we think
Yeah.
cheating is bad? Because cheating gives an extra advantage to someone which it shouldn't. That's why we keep talking about the fair comparison, and that fair comparison is extremely important for experiments like these as well. That's why same type of paper and same solvent. All right,
Yeah. Okay.
good, good. So I
Okay.
guess
Here,
that's it.
here is a question. Um, it's question number 5.
Okay, let's
It's the
move on to
same
question
thing.
number.
Yeah. Done. Scroll, scroll. Yeah. Still. No,
Okay,
no, no. The sixth one. Yeah, this
sixth
one.
one. Oh, all right, this one. Okay, I'm
Yeah.
gonna zoom it out a little bit so that I can see all of the questions along with it. Since this question has many
Yeah.
parts, now we can see all of it. Yes. Which one exactly do you want to ask questions for? Or do we need to go with all the parts of this question one by one?
We can do all.
Okay, in order to identify the writer of an anonymous letter, a sample of ink from the letter was dissolved in a solvent, then placed on some chromatography paper. Spots of ink from the pens of 5 possible writers, and the writers were G, M, P, R, and T, were placed next to the sample on the chromatography paper. They are going to come up with a scenario like this in order to ask questions. So the final chromatogram looks something like this. Okay, now we have the letter and the possible colors of that is the dye or the ink composed of. Then we have G and M and P, R, T, the possible writers. All right. So number A,
Yeah.
which of the 5 writers is using ink that matches the sample from the letter? Now, in order to get those 5 out of those 5, in order to pick one, it should have most spots similar to this one, and this one. So which one that is? Compare the lines, you will
It's
get
M.
right. You did it correctly in the first attempt because you knew that this one matches to this one matches to this one, and this one matches to this one. There you go. All of these belong to M. You did the same
M.
solution, right?
Yeah.
Great. Let's come to part
Yes.
B. Which of the writers is using a pen that contains ink made from a single dye? Single dye means it should give you a single spot and not too many spots.
Just a single.
Yes, it only gives us one color as a result. Single means one
Is
color.
it R?
Perfect. R is the only one which gives us a single color. Let's move on to the next one. C. What is the RF value of blue dye in suspect P's pen? All
Okay.
right.
I'll do this.
So
Yeah.
you can do it with scale. Let's not do it completely right now, but I guess I hope you understand that this can be the
Yeah.
X
Yeah.
and this whole thing can be the Y, and dividing X from Y will give you the answer, right?
Yes.
And from the center of it, you are going to take this number and you're going to take this number. The numbers are already written over here, so it shouldn't be a problem. This is like 1.8 or 1.9. I guess this is 1.8. This is 4. 1.8 divided by 4 will give you the answer, right? Whatever the answer may be, we're not
Yes.
exactly calculating it right away, but I hope you do get the idea what we need to do. Okay.
Yep.
So D, which two of the five writers are using pens containing the same ink? I'm going to clear it all up so that you get an idea. Which two of these five writers are using pens that contain the same inks? Same inks means they give us exactly same colors at exactly same positions.
Wait, okay. Um, using this.
Same ink, GMPRT. Out of these five writers, there are two which gives us exactly same results. The same number of spots at the same heights with the same colors.
Okay, is it G and T?
Perfect, right? Great. So
Yeah.
let's move on to the last question. Whose pen contained the dye that was most soluble in the solvent? Remember, the most soluble one tends to go as near to the solvent front, containing the farthest distance as possible, covering the farthest distance, of course.
Okay, so it's P.
Great. Now you have solved almost every type of question there is for chromatography. I hope you're
Yeah.
confident that you can solve any type of question, whether it's about solubility, whether it's about calculation of an RF value, whether it's about whether it composes of a single substance or more substances, or which two substances can be the same. Whatever the question may be, I think you can get it now, since you have done all of them
Yeah.
correctly, right? I hope
Yeah.
you are as confident as I'm talking about you being confident, right? And this
Let's
actually
hope so.
finishes the whole chapter as well as the exercise for us. Any more questions?
No.
It's about time. So what we are going to do is that we are going to